Hello and welcome to this video. In this video we are going to be looking at the sources of background radiation. Now we've looked at these types of radiation before where we're looking at alpha, beta and gamma radiation, and we've said that these have different ranges, but things like gamma radiation, or basically any of the electromagnetic radiation, will all have infinite range, which means if they've been emitted from some nucleus somewhere in the universe, eventually at some point it's going to pass through your body, okay? Because again, these unless it's absorbed by some material, and that means that actually radiation is all around us. There's radiation everywhere, and this is what's known as background radiation. So this is radiation that just exists in the universe because of certain sources of these types of radiation. It's not of a level that is harmful because everyone's still alive, but it is of a level that we can actually detect it and make measurements of it. So what we're going to do in this video is first look at some examples of the biggest sources of radiation or background radiation, and then we're going to follow on from that by trying to see how we can still make accurate measurements of radioactive sources while we have this background radiation going on. So let's first look at some sources of background radiation, and I'm going to list them in order of the highest amount of radiation given out to the lowest amount of radiation given out, or highest amount of background radiation that it contributes. So the first and biggest contributor to background radiation is actually air. Now, air has a very, very small percentage of radon. Now, radon gas is a type of radioactive gas. Now, it only makes up like 0.4% of the, or 0.4 to 0.8% of the atmosphere. But if we then think of the entire volume of our atmosphere, 0.8% of that is still a pretty large volume. So it still contributes the largest amount of background radiation to what we can measure. Obviously, this again is not to a harmful level, but air will give us the largest amount of radiation. The second largest comes from medical uses of radiation. Now, as we've seen in previous videos, we have processes such as cancer treatment, cancer treatment. It's used for sterilization. We have a lot of different uses for radiation in medicine, and because we're using those in almost every hospital that we have around us, that then means that we're going to have pretty large excess radiation that's just going to be existing because of background radiation. After this, certain rocks or the ground will also give off small amounts of radiation, since some of the elements that make up the core of the earth or our ground are inherently radioactive to some degree, and hence if they start to decay, even if their half-life is maybe 1,000 years and they only decay maybe once every year and emit one single piece of radiation, it's still contributing overall to our background radiation. And after this, we then move on to food. Food is a massive thing in the world because we literally all need it to survive. But certain foods you may be aware of, things like bananas, which contain potassium, which has the chemical symbol K. These give out very small levels of radiation. So if you've ever eaten a banana, you've been exposed to radiation inside your body. There's then bigger sources like cosmic rays. Now, cosmic rays can be made up of a few things. We can get things like solar flares that come out from the sun for us, or other maybe gamma ray bursts from distant stars, or maybe even just CMBR, which is cosmic microwave background radiation. and cosmic microwave background radiation is believed to be just the radiation that was given out after the Big Bang, and it's just the excess that we see permeating all of space. And again, we can physically measure this. If you've ever seen static on a television or heard static on the radio, that static is actually the detector of the TV or the radio actually picking up this cosmic microwave background radiation, and it causes the interference of the signal. Now we can also go on and say, of course, a big type of radiation is from nuclear weapons or even nuclear power plants, because if we are using radiation, it's not 100% certain that all of it is being absorbed, especially in a nuclear weapon. For example, atomic bombs when they were dropped, or nuclear weapons that exist currently or are being tested or anything like that. Whenever that happens, that emits radiation across not only our planet but actually our universe. And so this will then contribute to background radiation that exists. And the last one, the smallest amount, is air travel. When people travel by aeroplane or something similar to this, or even spaceships, there's usually very small amounts of radiation involved. Most of these will be electromagnetic types of radiation. It's very rare to get any kind of alpha or beta decays out of these. Then these make up all of our sources, or our biggest sources of background radiation. Now you do have to know these. You don't have to memorize all of them in their exact order. I would probably recommend knowing 3 or 4 different examples. It's a very common exam question on this topic to just ask you to state a possible source of background radiation with some reasoning. So if you know 3 or 4 of these, then you're pretty set for one of those questions, because sometimes they may say air and medical equipment are 2 sources of background radiation, name 1 more, and so on. Okay, so sometimes they'll miss out, or they'll already use the ones that you're aware of, so it's good to know 3 or 4 of these just to be prepared. Now from here we have to then say that if this is present in our universe, when we detect radiation, how are we certain that that source is emitting radiation and it's not just radiation that exists because it's background radiation? How can we actually tell the difference? And the truth is that it's very difficult to actually tell the difference. If we were to just set up a detector, which we call a Geiger counter, or is sometimes referred to as a Geiger-Marsden counter, the whole purpose of a Geiger-Marsden counter is to simply detect each individual radioactive particle, and in doing that it adds to a count, and that count will continue going until you stop the detector working. So it just counts the incident radiation. So whether that's gamma rays or anything alpha or beta, it will just add it to a count. Now, if we just take one of these Geiger counters and we leave it out in a room that we suspect has no radiation in it, it will produce some count. And the count that it produces will be entirely based off of the background radiation that exists in that room. So then, if a Geiger counter is left in a room, it will inherently, Geiger spelled like this, it will inherently count background radiation. Now, the background radiation, in comparison to detecting radiation from an emitting source, will be preferably a very small number. If we had very high levels of background radiation, the Earth would not be a safe place to live. So usually the background radiation count is kind of a small value. What this means is we have to then use this as a kind of offset whenever we take radiation readings, and this is called the corrected count rate. Usually when we are measuring things like activity of certain radioactive particles or sources, we make a count rate. We see how quickly is this stuff decaying in order to release these radioactive particles. What we're saying here is we have to now say all of these readings that we have are also produced with some offset, because we aren't certain that our detector is only measuring the radiation due to that source. It's also measuring radiation because of background radiation, which means we have to always set up 2 Geiger counters, and we'll have one that is facing towards the source. So maybe this is our source, and we have they're usually Geiger tubes that will be connected to some sort of counter. We'll have one directly towards this, and it will be in a lead lined box so that only the radiation can come out and go straight into here. And then we'll have a second counter that will be somewhere else in the room, and that counter's purpose will be to detect any background radiation. So its whole purpose is to detect background radiation. Now, we get 2 count rates. We get one from our first detector, which is detecting the radiation straight from the source, and we get one from our second detector, which is measuring the background radiation. Now, we are basically 100% certain at this point, if this Geiger counter 1 is directly facing a radioactive source, it will detect more radiation than the background radiation. What this means is that our actual level of radiation that we can detect from this source, our corrected count rate, is the count rate from 1, which I'm just going to call the count rate, minus the background count rate, which I'm going to call the background count. And this is essential. This must be calculated whenever we make any measurement of this. And this will come up again when we look at the required practical on this topic, where you will actually handle some radioactive source, and you will be asked to make these kind of measurements of the corrected count rate, and you will have to come up with some level of background count for the room that you're in at the time. So just to recap what we've done, we've looked at some example sources of background radiation, and then we've said that due to these sources of background radiation, we have to make sure when we're making measurements in a lab, we have to correct these measurements by taking a background reading as well as our actual reading. The difference between those is then called our corrected count rate, and that is the thing that we want to use in a graph or as our actual measurement of radioactivity or activity. Thank you for watching.